Okay, all right. Last class, if you can recollect, we have started with the general feedback structure, and remember the module that we are covering is module 3. Let me show the beginning. Module 3, the title of the module is feedback amplifiers. In that last class, we have covered a few definitions, okay, for feedback. Then a illustration of feedback definition through the flow chart. Following with we have covered types of feedback, namely negative feedback and positive feedback, and we have given examples under each of this category. For negative feedback, common source amplifier with RS is best example, and for positive feedback, which is also called as regenerative feedback, the examples for that is an oscillator and even multivibrators also. Later we have explained negative feedback and positive feedback through the flow diagram. Primarily this whether negative feedback or positive feedback comprises 4 building blocks: source block, amplifier, basic amplifier. This can be a BJT based or it can be an FET based amplifier. Then we have a load which is connected to the amplifier. In general way, it is connected to the feedback amplifier, and there is a feedback network which is whose gain is defined by beta. And here we can see the loop here. Okay, the loop is formed by the source, amplifier, load, and the feedback network. Okay, so we'll discuss this loop gain later. And this is general negative feedback, a flow diagram. The negative feedback is because there is a negative signal. I mean the phase shifted signal is coming in series with the source signal. That's why it's negative sign here. And for the positive feedback, there is a in phase signal which is coming from the feedback network with the gain beta, that's positive, that gets in series with the source signal, that get added through the mixer here. The summation denotes here the mixer. Okay, so this is the flow diagram for signal flow diagram for the positive feedback. And a couple of advantages of positive feedback we mentioned in the last class. Generally we have mentioned. Later on we will take up these properties of negative feedback in detail. It desensitizes the gain, because the amplifier gain depends on several parameters. Output keeps varying. Output is so sensitive. So in order to desensitize the gain of the amplifier because of its dependence on temperature and other parameters, this negative feedback plays an important role. Negative feedback also reduces nonlinear distortions like harmonic distortions. Usually in the output, the waveform replicates the fundamental frequency. Okay, so in order to cut down or reduce this a repetitive frequency of waves of fundamental frequency, we use negative feedback. That's called nonlinear distortion. So since nonlinear distortion is due to the a basic device used in amplifier is either BJT or MOSFET, those two devices are nonlinear in nature. Due to the nonlinearity of fundamental device, the entire amplifier exhibits nonlinear distortion. This nonlinear distortions can be overcome by using a negative feedback. The noise effect can be reduced by the negative feedback. Okay, so the noise can be either internally generated or external noise. So those can be minimized using a negative feedback amplifier, and we can have a good control over input and output impedances, with reference to the amplifier. Okay, and also there is an extended bandwidth in case of negative feedback amplifier. All these things we are obtaining at the cost that we are paying is reduction in the gain. Okay, the gain reduction factor is also called by the another terminology which is called as amount of feedback. Okay, so these are the few things that we have discussed in the last class. Coming to general feedback structure, again you have seen this all 4 building blocks in the feedback structure. Throughout this chapter we will be using these 4 blocks frequently. So students should be familiar with whenever we say feedback, you should be familiar with all these 4 blocks here. and only difference is whenever we apply negative feedback there will be a negative sign here, and for the positive feedback there will be a positive sign here. 90% of the time we will be discussing about negative feedback, since already we have covered positive feedback in oscillator circuit. Okay, so students should be familiar with this block diagram. Okay, so there is a negative feedback you can see make out here. Okay, let me use here. Okay, so this is these 4 blocks, student should be familiar here. Okay, so this is I am highlighting those 4 blocks which are important, which you should remember, and also the sign here which you should not forget here. There is a negative sign here for the negative feedback amplifier, and all these signals also you should be aware. So we have here XS, XI, XF, X0, and also gains. You can see the basic amplifier gain we have denoted as capital A, uppercase A here, and beta is the gain of the feedback network. Okay, feedback circuit. Okay, this is a general feedback structure. Okay. Next, we have illustrated this step by step by splitting of this each blocks, especially the mixer here, the sampler, and there is an amplifier, there is a beta network. All these things we have discussed in the last class. So I don't want to spend time on this. We'll move on to the straight away to the, and importantly we have discussed the expression for the gain with negative feedback. As you can see here, AF is a gain with feedback, okay, which is by definition it is X0 by XS. X0 is the output signal. It can be current or voltage. That's why we denote it here with general notation as X here. X means it can be voltage and it can be current. Instead of indicating V0 by Vs here, we are showing here as X0 by Xs. Okay, so this is general signals, output signal by the input signal, which is A divided by 1 plus A beta. Okay, denominator you can see that there is a 1 plus A beta term, that shows that gain with feedback is reduced by this much amount here. The denominator term what you see here, by this much amount gain with feedback is reduced. So though we have reduced the gain, but on the other side you get many more advantages. So there is a compromise or trade-off exists between the gain and other advantages or benefits you are going to get from this amplifier. So comparing this AF and A, definitely AF will be less than A. This is for the negative feedback. You can see that there is a positive sign in the denominator. There is a 1 plus A beta. Whereas for positive feedback you will have negative sign here. Okay, so 1 minus A beta. So these gain expressions you should remember for both positive feedback and negative feedback here. This is the gain for negative feedback. Okay, these two gain expressions you should be familiar. Okay, students often confuse with this positive sign and negative sign. I have seen that. Since there are various formulas you will come across in this module, so there is chances of confusions are very high. So I would suggest note down all these formulas at the end of your notes or material, so that you can memorize them before the examinations. Frequently memorization will help you in remembering for a long time. Okay, so this is the expression for gain with feedback for the positive feedback amplifier. AF is equal to A divided by 1 minus A beta. And now we can have here the comparison between this AF and A here. If we compare these two things, so AF is going to be greater than A for the positive feedback amplifier. Okay, we have solved this problem in the last class. I don't want to spend time on this. Loop gain also we have seen. Okay, so in the feedback general feedback structure, okay, we have here source signal will go through the basic amplifier, and we are sampling here the output signal and bringing back to the feedback network, and then it gets mixed with the mixer here. So there is a loop here which you can see here. The loop gain is a product of A into beta. Okay, so this loop gain for a positive feedback it will be greater than 1. So we have seen this in Barkosian criterion. Generally for the negative feedback amplifier, loop gain will be negative. So loop gain is minus A beta. A beta is called as loop gain, and since it is going to be negative for the negative feedback amplifier. Okay, we have explained here, which you can go through that, and I will just highlight the important things which is required for your reference here. The 1 plus A beta, we have another terminology called return difference, which we call here as 1 plus A beta. You have seen this 1 plus A beta in various formulas, as you can see here. 1 plus A beta in gain equations, you can see here 1 plus A beta. So this 1 plus A beta is denoted with another term called as return difference that you are seeing here. You can see return difference is nothing but labeled as 1 plus A beta. As I mentioned in the beginning, you will come across several formulas, so students should remember this. Sometimes in examination they may ask you to calculate return difference, so you must use this 1 plus A beta. Okay, the amount of feedback introduced into an amplifier you can also express in decibels. Okay, so n is the value depends, it's positive means it's a positive feedback, n value is negative means it is a negative feedback. Okay, so therefore this n value can be expressed in decibels as 20 log of AF by A. Okay, so this is AF by A is nothing but, as per our gain equation, it is 1 divided by 1 plus A beta. Okay, so here these formulas, once you are familiar, you can directly substitute here and find out the equation, final equation for the n. N is nothing but amount of feedback introduced into an amplifier. Okay, n is negative means it is negative feedback amplifier. If n is positive, it's a positive feedback amplifier. Okay, now we have a few problems to solve here. Just to minimize this, let's take up this problem here. A closed loop, calculate the closed loop gain of negative feedback amplifier if its open loop gain is 100,000 and feedback factor is beta. Okay, whenever you see these type of problems in examination or somewhere else, you can write down the given data, what is given and what is asked here. So in this problem it is asked to calculate the closed loop gain. It straight away we can know that it is asked for AF or AVF. Okay, so write down the given data. A is given basic amplifier gain or open loop amplifier gain is given A, which is 100,000, and gain of the feedback network is also given, which is 0.01. Okay, so using these two relations, you can substitute in the formula basic gain equation, which is AVF is equal to A divided by 1 plus A beta, and you can obtain the gain with feedback, which is going to be 99.99. so this is the gain with the feedback. And now you can see the gain without feedback, which is 100,000, and gain with feedback is 99.99. so see the amount of gain reduced, from 100,000 it has come back all the way to 99.99. so this clears that the gain with the feedback is reduced when we compare the gain without feedback. Okay, so the next is the voltage gain without negative feedback is 40 dB. What is the new gain if 3% negative feedback is introduced? This is the next problem. In this it is asked here, the voltage gain with negative feedback is 40 dB. Remember that it is given here in 40 decibels here. So you should be aware of these things whenever you solve any problem. Okay, so it is given in 40 dB, that is the gain without negative feedback, that is A, which is given in 40 dB, and 3% negative feedback is introduced. Okay, it's told in the problem that there is a 3%. So 3% means it is a 0.03 or 3 by 100 that you can do in that way. So that gives me beta as a 0.03. Since A is given in decibels, you can convert back to the normal value by using 10 log of AV, which is equivalent to the 40 dB. So AV becomes the 10,000. You can now substitute here AV in this basic formula, A divided by 1 plus A beta. Okay, so value you can calculate, you can substitute A. We need to calculate AVF, which is 33.22 by substituting these values. Okay, like this there are several problems are there. I look forward students to go through all these problems and solve these problems and become familiar with these problems here. Okay, so I don't want to spend time on these problems. So I look forward for students to solve each of these problems. Okay, with that let me move on to the properties of negative feedback. That is the highlight of today's class. Okay, so in the properties of negative feedback, first we will take up gain desensitivity. Okay, so let us define what do we mean by gain desensitivity. The gain of the amplifier is not a constant. We are already familiar with that. The gain of an amplifier depends on several parameters here. Okay, what are those parameters? The number one is the operating point. The gain depends on the operating point. Either it is a BJT based amplifier or an FET based amplifier. Gain depends on the operating point, and also gain depends on temperature as well. So now here, since this amplifier is so sensitive to these parameters, how do we desensitize that? So that will happen in the negative feedback amplifier. So that factor is called as desensitivity factor. Let us see that how this, to what extent the amplifier with feedback reduces the sensitivity. Or another way we can call this as desensitivity. More the desensitivity, the amplifier is stable. We expect this desensitivity factor to be as high as possible. Okay, so that improves the stability. Now in a practical amplifier, what you see is the gain of an amplifier depends on these factors like operating point, the temperature, and even other parameters like the beta depends on various parameters with reference to BJT, and that is a lack of stability. That lacks stability of an amplifier, and this can be reduced by introducing the negative feedback. Okay, so we will see that in a couple of seconds later. Okay, so now we will just take this basic gain equation. So again I stress once again, these equations students should memorize here. Okay, there is no shortcut. This entire chapters is based on only the previous equations. Okay, so just recall this equation. Gain with feedback is A divided by 1 plus A beta. This is plus, means it is for negative feedback. So let us use this equation and show that how this negative feedback reduces the sensitivity and increases desensitivity. Okay, that factor will prove it here. Now using this equation, we are going to differentiate this with respect to the basic amplifier gain A. I hope you all know how to differentiate this equation, which is this equation just looks like x divided by 1 plus x into some constant here. So you all know how to differentiate these kind of equations. So we will do here differentiation for this equation and see the results of that equation. Okay, so DAF by A, DA, we are differentiating this AF with reference to A amplifier, basic amplifier gain A, which is equivalent to the denominator we have 1 plus A beta square whole square, and the numerator will have 1 plus A beta is kept as it is, that is the denominator term, and we are going to differentiate this this A, okay, with reference to A only, which gives us 1, and minus as it is. Okay, this is as per the differentiation formula, we are using minus sign here, and differentiation of this entire factor gives 1 is nothing but 0, and we have left out with A beta. So differentiation is DAF by DA is nothing but 1 plus A beta minus A beta by 1 plus A beta whole square. Further is only simplification, so students should be familiar with this differentiation formula, so that you easily do this derivation. See, at least 3 to 4 derivations will be asked in examination. Students should be familiar with all these necessary equations and their respective derivations. Okay, so whenever they ask about properties of negative feedback, generally whichever the properties you can illustrate, or sometimes they may ask you specific negative feedback properties also. All right, let us see that how to simplify this after differentiating with respect to the basic amplifier gain. So in the left hand side we have just an DAF by A, that is the DA by, that's kept as it is, and numerator you can see that A beta cancels off here, and you are left out with 1 divided by 1 plus A beta whole square. Okay, so that is in the left hand side, you can see we have still DAF by DA, and you can transfer this DA to the right hand side. So the final formula for after differentiating and rearrangement, you will see DAF equals DA divided by 1 plus A beta square. We can bring this equation into the standard form. Again we will do some rearrangement. Okay, so for that we need to divide both the sides of both the left hand side and right hand side by the factor called AF. So we have here on the left hand side DAF by AF. Look at this, what we are doing, I am just showing here in the before the next step. So we are just dividing both the sides of both sides, means LHS and RHS by AF. So, you can see a DAF by AF, which is equivalent to DA by 1 plus A beta whole square into 1 by AF. Okay. So, now we know what is AF, this okay, AF gain with feedback, basic amplifier, the amplifier with feedback gain is given by A divided by 1 plus A beta. Now, we can substitute this here. Okay. So, what you get it here after substituting, which is shown here. So, left hand side DAF by AF is kept as it is, right hand side DA by 1 plus A beta square also retained as it is, but now look at here, AF is nothing but A divided by 1 plus A beta. So, here if you substitute A in the denominator, 1 plus A beta goes to numerator and 1 plus A beta cancels with this 1 plus A beta square, one term you are going to reduce here. So, finally, we have here, we can rearrange these terms, DA by A is indicated in a bracket here, and we have left out in the denominator as 1 plus A beta. So, it is 1 divided by 1 plus A beta. Okay. Now, we can introduce another term which we already said, it is a return factor, a return difference. Now, we are the same return difference D is also called as desensitivity factor here, the same return difference that we have mentioned earlier, here it is called as desensitivity factor. So, desensitivity factor is nothing but 1 plus A beta. I am defining here, okay, this is a definition, okay, not any proof of any equation, this is a definition. The desensitivity factor definition is, it is 1 plus A beta. Okay, desensitivity factor is reciprocal of sensitivity. If I say this D and S here, S is nothing but sensitivity, is equal to 1 by desensitivity. Okay, 1 by desensitivity. Okay, so this is desensitivity 1 plus A beta, right. So, let us now substitute this desensitivity definition in this derived formula. So, what do you get here? So, on the left hand side you have DAF by AF as it is, and on the right hand side you can see this factor we have retained DA by A, but look at here, this changes we have introduced here the desensitivity factor, which is D. Okay, so D here. Now, this is the final equation. As I told you, we have to bring always equations into the standard form, so that we can define the importance of that equation. Okay, so look at this equation, and you can easily say that how this negative feedback reduces the sensitivity or increases desensitivity. Left hand side, if you observe, there is a DAF by AF, which is nothing but it's a fractional change in the amplification with feedback. Okay, and in the right hand side you can see that we have a DA by A, which is nothing but it's a fractional change of an amplification without feedback. You can also indicate DA means it's a change in basic amplifier gain by the amplifier gain, and here you can say that change in amplifier gain with feedback divided by gain of an amplifier with feedback. In that way also we can indicate, we can illustrate. Okay, into that's multiplied by the 1 by desensitivity factor, which is D. Remember, desensitivity and sensitivity is reciprocal of each other, and higher the desensitivity, sensitivity becomes less, sensitivity reduces. We expect this desensitivity factor to be as high as possible, so that we will have a less sensitivity. Amplifier should not be sensitive, amplifier should be robust, amplifier should provide constant gain, amplifier should be stable. More the stable amplifier, you get very good response for that. Okay. So, looking at equation 3, we can say that change in gain with feedback is less than the change in gain without feedback by the factor of 1 plus A beta. This is what we have seen here. Okay. And also we can rearrange this. As I told you, sensitivity is 1 by D, 1 by 1 plus A beta. Desensitivity is D, which is equal to 1 plus A beta. Now, same equation we are just rearranging, which you can see DAF by AF, and this factor we are transferring to the right hand side, left hand side, and what you get is DAF by AF is divided by DA by A, which is equal to 1 by D, 1 by 1 plus A beta. So, this shows that the stability of an amplifier increases with increase in the desensitivity factor. Okay, there is an increase in the desensitivity factor, so that increases the stability of an amplifier here. And also there is another relation which is important here in the basic gain equation. Okay, if I assume that A beta loop gain, if it is far greater than 1, if we adjust the amplifier and the feedback network such that if we are able to achieve this, okay, the product of basic amplifier gain and the feedback network gain, if we can make it more than 1, then let us see what is its effect on the negative feedback amplifier gain. So, if I apply this assumption here into this formula, what happens now? So, this shows that this 1 can be neglected in this equation. So, if you neglect 1 here, this A cancels with this A, and what you left out is just 1 by beta. Now, see here, gain with feedback only depends on the beta. Okay, that means it is independent of okay, the amplifier gain A. Okay, even though there is a change in amplifier, okay, amplifier due to the some variations in parameters, here there is no A factor at all. Okay, so therefore, A purely depends on beta network. This happens only under this condition. Okay, that means if you are able to maintain the loop gain greater than unity, then this is possible. We can make gain which the gain of with feedback is it's not sensitive, or you can say it's insensitive to the amplifier parameters, okay, that you can achieve by meeting these conditions here. Okay. So, gain with feedback is dependent only on the feedback network. That is the outcome of this assumption. Okay, let us take up this problem based on this negative feedback. Every property, we will have 1 or 2 problems, so that you can understand the concept behind the property. Let us read the problem for you. An amplifier has an open loop gain of 1000, that is A, which is given as 1000, and a feedback ratio of 0.04, which is 4% feedback ratio is given, beta is given as 4% or 0.04. If the open loop gain changes by 10% due to temperature, that means A is, that is said in the problem, it is changed by 10% due to the temperature variation, and it is asked here, find the percentage change in the gain of the amplifier with feedback. That means if you introduce a feedback to the amplifier, what is the percentage change in the gain? That is what we need to calculate here. Okay, now let us write down the given data. Okay, so A is given as 1000, beta is 4% or 0.04, and you can see that if the open loop gain changes by 10%, it is said here. So, change in open loop gain, okay, is dA by A is nothing but 10. Okay. So, now we can use this equation which we have derived here, dAf by AF is equal to dA by A into 1 by 1 plus A beta, and you can substitute for dA by A and all other things, and you can calculate what is dAf by AF. As you can see, it is just a 0.25%. If you simplify this, you will end up with only 0.25%. What do you mean by that? Just it is a sorry, there is a 0.25% change in the gain with when we introduce the negative feedback here. So, without negative feedback, you can see that there is a 10% change due to the temperature, and with the negative feedback, the percentage change has been reduced. That means the amplifier is very much sensitive to the temperature without the feedback, and the sensitivity can be brought down by providing a negative feedback. How much in this problem? It is 25%, 0.25%, not 25%, it is 0.25%. Okay, so that means you can see that how much it has been reduced here. From 10% we have brought down to the 0.25%. That is the first property, and I hope the concept is clear with reference to the first property. Any questions are there? I am glad to answer your queries. Okay. Okay, all right, let us move on to the second property, bandwidth extension. This is also an important property. From this property, we will illustrate how bandwidth get extended by using negative feedback. Okay, yes, a bit of assumptions are required. A few equations I am using from from the textbook of Cedra Smith. Okay, so bandwidth extension, we can characterize high frequency response. So, now you should be familiar with high frequency response of an amplifier by a single pole. Okay, I hope you understand this. The transfer function of an amplifier especially at high frequency response, it can be characterized by a single pole. I hope the students are familiar with zeros and poles. Okay, are you do you have studied anywhere else the poles and zero concept? Whatever we see in the numerator, the root is nothing but a zero, and denominator the root is nothing but called as a pole. Okay, I am just giving simple definitions here, that's all. Okay, any transfer function which is made up of both zeros and poles. Okay, but here we are specific to the high frequency response, that we can characterize by single pole here. That is the property of this high frequency response of an amplifier. So let us now write the equation for the gain at mid frequency and high frequency. We can express it with this, because in high frequency response, since it is characterized by single pole, we can write the gain equation AFS. We can see that gain now is a function of variable s here. S is nothing but it's a Laplacian domain. Okay, AFS is nothing but gain in Laplacian domain, which is equivalent to the AM divided by 1 plus S divided by omega h. So this equation is just an usage. I am using this equation, high frequency response equation here, because using this I am going to prove how bandwidth get extended by applying the negative feedback. So this is just a transfer function or gain of this of a high frequency amplifier. Okay, AM is nothing but which is a mid band gain, and omega h is nothing but it is a upper 3 dB frequency of the amplifier frequency response here. Okay, so this is called as the pole. You can see there is a pole. Okay, so the root of this can be called as a pole. Our denominator part can be called as a pole here. Okay, so now using this equation we can now show that how bandwidth get extended. Okay, any questions about this? This is the equation, just I am using it from the high frequency response. Okay, so students should go through the high frequency response, and this is a general equation I am considering here, and using this we are going to show how bandwidth get extended. Okay, now application of negative feedback with a frequency independent factor beta around this amplifier results in a closed loop gain AFFS is given by this equation. Okay, this is now with reference to negative feedback. Okay, so which can be written as okay, so AFFS is nothing but it is a gain with feedback in Laplace domain. Because why we move to Laplace domain, it's very important here. See, often we move between different domains. Okay, I hope you are familiar with a very popular domain called as a time domain. Okay, what are other domains you are familiar with? One is time domain, which is a basic domain. I can say that signals are often represented in time domain. Okay, when you see a graph of amplitude with reference to the time here, okay, so that is called as a time domain. Okay, so amplitude with reference to the time, so it can be time. Okay, so this is an amplitude. When I say amplitude, it can be the voltage or current. Okay, this is a time domain here, right? But like this we have other domains also. There is a frequency domain. Okay, frequency domain, we plot gain as a function of frequency. And another domain which is very popular is the S domain. Okay, S domain. There are even other domains also, Z domain. So this you will get familiar when you move to higher semester. Students need not worry about these domains. Okay, time domain, frequency domain, S domain, Z domain, all these things. Here we are using S domain because it's very easy for us to interpret signals. Whenever we represent signal in time domain, we can also convert into frequency domain, then into S domain, then into Z domain. It is possible. There is no change in the signal when we move from one domain to another domain. Okay, so that's why you might have seen in our derivation, often we move between time domain to S domain and S domain to the time domain back, vice versa. The domains are useful to sometimes to simplify equations or sometimes to ease the derivation. Okay, so here the very popular domain to simplify the transfer function is S domain. Okay, so even in the back you have seen that this transfer function of high frequency or high pass filter is represented by this transfer function given by AFS, which is AM divided by 1 plus S by omega h. This is the transfer function of an high pass filter, okay, which contains the one pole here, okay, and no zeros here, okay. Like that we can for a negative feedback amplifier also we can write gain equation as AS divided by 1 plus A beta. You are already familiar with A divided by 1 plus A beta, but wherever there is a gain, we have added here subscript as not subscript, it is a S as the parameter here. This shows that we are in S domain. Okay, earlier without writing this, it is a time domain only. Okay, that's a thing which student should be familiar with. Okay, this formula is straight away written based on the gain with feedback A divided by 1 plus A beta. Okay, now we can substitute this equation in 1. Okay, so 1 you can substitute what we get. Let us see here. This A is nothing but already we have defined here AFS. Now we can substitute in this equation 2. Let us see what we get here. AFS, which is a gain with feedback in the S domain, is kept as it is, and now in place of AFS, basic amplifier gain, now we are looking at just an high pass frequency response. Okay, so AFS is now high frequency response is now written in terms of gain equation as this: AM divided by 1 plus S divided by omega h, and here also we have an AFS. We can also substitute here same equation: AM divided by 1 plus S into S by omega h. Now we can see the advantage of using S domain is just by simply substituting S as j omega, we can move into frequency domain. So as I told you that it's very easy to move from S domain to frequency domain to the time domain. So here the importance is we need to visualize signals in the frequency domain. So therefore we have started with the S domain, which is here. Okay, then we are moving directly to the frequency domain by just substituting S as j omega. Okay, wherever there is a S here, you can substitute as j omega. So in the left hand side you can see AF of S means it is AF of j omega, that is left hand side, and right hand side you can see that we have replaced j S by j omega. This is the equation: j omega by omega h. Omega h is nothing but higher cutoff frequency. We have seen this in the oscillator circuit as well. Okay, since we are dealing with high frequency response, this is the transfer function for the high frequency response high pass filter. So this is what you can say, the equation which is resulting. Okay, so now we can take LCM in the denominator and simplify this. Okay, so we keep numerator as it is. We don't want to make change in the numerator, but in the denominator you can see when we take LCM here, so 1 plus j omega by omega h is retained in the denominator, whereas here you can see it's get multiplied 1 plus j omega by omega h plus beta AM is kept as it is. So this 1 plus j by omega h cancels with this from both numerator and denominator, and the remaining terms are shown here. Okay, so this is simply mathematical derivation. Okay, AM divided by 1 plus j omega by omega h plus beta AM, and now we can divide numerator and denominator by this. As I told you that when we are doing these kind of changes, okay, so student should remember that we are doing for representing in a standard form. So for that we need to divide numerator and denominator by AM 1 plus AM into beta. So you can see that after doing that, the resulting equation is as shown here. Okay, and further you can see that you can bring back the S here wherever there is a j omega. Okay, so numerator you can see we have retained same term. Okay, what you are seeing here, and in our denominator you can see that we have written S by omega h. You can take out common factors here, S by omega h in this thing, and what you get here is 1 plus as it is. So otherwise you can divide 1 plus AM into beta. So here also we have 1 here, AM into beta is there. Okay, if you just split this, 1 plus am beta, 1 plus am beta cancels, you are left out with only 1, and this j omega by omega h is now multiplied with 1 by 1 plus am into beta. That is what you are seeing here. Okay. Next is we can indicate this j omega as s. That is what you see here. So final equation is a of s is equal to am divided by 1 plus am into beta. In denominator we have 1 plus s into s by omega h into 1 by, divided by 1 plus omega am into beta. Now we can compare this with the basic equation what we have defined. So this is the basic equation. So you can see now here this the basic equation, when we compare equation 1 and equation 3, for your reference I have written here the equation 1 here, and when you compare this with this equation, this is the for the feedback and this is without feedback here. Okay, so we can write the gain with feedback as AMF as this term numerator, AM divided by 1 plus AM into beta. This is the gain with feedback, or you can say the amplifier gain with feedback is a midband gain of a feedback amplifier is given by this equation. And when you look at the cutoff frequency omega hf, that can be written as omega h into 1 plus am into beta, this factor, denominator factor, omega h into 1 plus am into beta. So what this shows here? This shows that gain the frequency with feedback is nothing but increased by 1 plus am into beta. Okay, increasing upper cutoff frequency, and if you do same way the lower frequency response also, you will get this factor in the denominator. So like this, we are not done for lower cutoff frequency, but we say that similar to what we have done for upper cutoff frequency, we can also do it for lower cutoff frequency. Upper cutoff frequency with feedback is increasing, lower cutoff frequency with feedback is decreasing. What happens now? Upper cutoff frequency increases, lower cutoff frequency decreases. This shows that bandwidth is increasing. So you can see here, this is the frequency response. Okay, so this is a gain without feedback. The gain with feedback, you can see there is a drop in the gain because there is a drop by an amount of 1 plus am into beta. And look at now here the high frequency response. Okay, so here the 3 dB frequency for without feedback will be somewhere here. Now it has increased here because higher cutoff frequency has been increased here by 1 plus am into beta. Okay, this shows that the bandwidth has been increased with the negative feedback. I will stop it here, and we have discussed today two important properties. One is desensitivity and other one is extended bandwidth. So students should be familiar with these two properties. In coming class we will discuss on other important properties like noise reduction and distortion reduction. Okay. With that I will stop here, and any questions can be taken offline.